All right, welcome back to the Explainer. Today, we are jumping into a real beast of a problem, count of range sum. Now, don't let the name scare you. It's an absolutely fantastic puzzle that layers a few powerful computer science tools together in a really elegant way. So let's just dive right in and break it down. So what's this problem all about? On the surface, it seems pretty simple, right? It's just asking how many different pieces of an array add up to a number that's within a certain range. But the real kicker, the thing that makes this a challenge, is the scale. The inputs can be massive, and that makes the obvious way of solving it totally impossible. Okay, first things first, let's nail down this idea of a range sum. It is exactly what it sounds like. You pick a start, you pick an end, and you just add up all the numbers in between. So for this little array, -2, 5, -1, the range sum from the beginning to the end is just 2. Simple as that.
So that's our mission, plain and simple. We need to find every single possible subarray, calculate its sum, and then just check, does that sum fall somewhere between our lower and upper values? If it does, we tick a box and increment our counter.
You know, the first thing that probably comes to mind is the brute force way. And it's a good place to start thinking. We could just write a couple of nested loops, right? One to pick the start point, one to pick the end point, and then maybe a third one to add up all the numbers in between. Check the sum, and boom. But, and this is a big but, here's where things get tricky. The problem statement says the input array can have up to 100,000 numbers. 100,000. As soon as you see a number that big, alarm bells should be going off. Any solution with nested loops is going to be dead in the water. So how slow is too slow? Well, let's do some back-of-the-napkin math. For an array with 100,000 elements, you're looking at roughly 10 billion possible subarrays. 10 billion! That's not going to run in a second or two. We're talking minutes, maybe even hours. We need a fundamentally smarter approach. Okay, so clearly that brute force method is a non-starter. The biggest bottleneck, we're calculating sums over and over and over again. We have to be smarter, and that brings us to our first tool. And that smarter way is a classic technique called prefix sums. If you haven't seen this before, it's a game changer. The basic idea is we do a little bit of work up front to create a new array of running totals. And with that array, we can find any range sum with just a single subtraction. No more loops. It's a huge win. So how does this actually work? Let's walk through it. We start with a 0, which kind of represents the sum of, well, nothing. Then we just go through our original array and keep a running total. So for -2, 5, -1, our prefix sum array becomes 0, -2, 3, 2. Now, if we want the sum from index 0 to 2, we just take s of 3 and subtract s of 0. Boom, 2 minus 0 equals 2. Done. Instant sum. All right, tool number 1 is in the bag. We can now get any range sum in a flash. This lets us completely rephrase the problem, and this is where it gets really clever. So let's go back to our original condition. We're hunting for any range sum that's between lower and upper. This is the core of the problem. Now, because we have our prefix sum array, let's just call it S for short, we can swap out that sum part. The whole thing becomes this neat little inequality. Lower is less than or equal to S of j minus S of I, which is less than or equal to upper. We've officially gotten rid of the summing loop. Okay, get ready for a bit of algebraic magic. Seriously, it's just a little rearranging, but it completely changes how we look at the problem. We're going to move things around to get Si, the prefix sum from the start of our range, all by itself. And boom, look at that. We've completely flipped the problem on its head. Now, instead of looking for a future range sum, we can iterate through our prefix sums one by one. And for each sum S sub j, we ask a totally new question. How many of the prefix sums I've already seen fall into this new calculated range? Okay, this is a huge step forward. But, there's always a but, isn't there? We've got another problem to solve. These prefix sum values themselves could be enormous, like billions or trillions, and really spread out. That makes them hard to work with. This is where a really cool trick called discretization comes in. The idea is, we don't actually care about the massive values of our prefix sums. We only care about how they stack up against each other, their relative order. So we gather up all the numbers that matter for our comparisons, sort them, and give each one a rank, starting from 1. So check out this table.
We take all the unique numbers that matter in our problem, sort them, and just assign them a new, small index. A value like 3 might become index 6. The original values are gone. All that matters now is their rank. We've basically squished this huge, sparse number line into a tidy little set of consecutive indices, which is perfect for our final tool.
We are so close. We have one last piece of this puzzle to put in place. We've turned our problem into this. For every number we see, how many numbers we've already seen fall into a specific range? How do we do that counting part? Fast. Well, we could just loop through all the numbers we've seen so far, but wait, that puts us right back at ON squared territory. No way. We need something much faster. And for that, we bring out the big guns, a data structure called a binary indexed tree, or a bit for short. So what is this thing? Honestly, just think of it like a super efficient accountant's ledger. It can do two things for us, and it does them ridiculously fast. First, we can update it. That's like telling the ledger, hey, just saw the number with rank 5, mark it down. And second, we can query it, asking, hey, how many numbers have you marked down that have a rank of 5 or less? Both of these operations are super fast. Okay, let's recap. We've got prefix sums for fast summing, we've got our rearranged inequality to change the question, we've got discretization to tame our numbers, and now we have a binary index tree for lightning fast counting. It's time to put it all together. So here's the grand finale, the algorithm itself. It's actually just one main loop. For every single prefix sum, S sub j, we do a few things. First, we use our fancy inequality to figure out the target range we're looking for. Then we use our discretize mapping to find the ranks for that range, let's say L and R. We ask our BIT, how many numbers are between rank L and R? It tells us the count in a blink. We add that count to our total answer. And finally, before moving on, we tell the BIT, okay, I've now officially seen the current number, S sub j, so add its rank to your ledger. We just repeat that for every number. Okay, let's trace this with our simple example to see it in action. We start with the first prefix sum 0. We ask our BIT about the target range, but since we haven't seen any numbers yet, the count is 0. Easy enough. Then we move to the next prefix sum, -2. We calculate its target range, which is -4, 0. Now we ask the BIT, hey, have you seen any numbers in that range? And it says, why yes, I've seen the number 0. So we add 1 to our total answer. See how it works? We just continue this process for every number, querying for what we've seen in the past, adding the count, and then updating the BIT with the current number. By the time we're done, we've correctly found all 3 valid ranges. So what's the big takeaway here? It's that we took this problem that looked almost impossible to solve efficiently, and we broke it down. We layered one clever idea on top of another. Prefix sums to stop recalculating, a little algebra to flip the question, discretization to tame our numbers, and a binary index tree to count things super fast. None of these tools on their own would have been enough, but together they create this really elegant and powerful solution, which kind of makes you wonder, right? What other tough counting problems out there could be cracked with